Yes, so on, if you're hoping you can see my first slide, at there's a table of contents there with some of the topics I'm going to go through today. One thing that occurred to me when I was writing these lectures is that a lot of the techniques we use are kind of fairly sort of generic to other types of data analysis more fundamentally. So the kind of things we do are not wholly different from what the kind of data analysis techniques they use for, say, looking for binary black holes, for example. So the same techniques of match filtering and template banks are kind of similar. So so hopefully you'll find this kind of introduction useful, even if you don't go on to study gravitational waves further. But if you are interested in the subject and you would like to continue your studies further, we'd certainly be very interested in having more people as part of the LIGO collaboration working in this area. I should say one of my other roles is one of the co-chairs of the LISC continuous wave group. So we'd be very welcome to join that group and participate in the work that we do. So the topic I'm going to cover is basically, I'm going to start with a very brief review of gravitational waves and general relativity, which some of you may have seen before, but I think it's useful just to sort of introduce that. Then we'll go a little bit through the continuous wave signal model, and then look at techniques called match filtering and something called the F-statistic, which is something that was quite fundamental to what we do. And we'll look at some properties of that, in particular, the probability distribution. And then finally, we'll look at some template, the idea of template banks and something called the parameter space metric. So I'll probably try and go through for about an hour and then maybe have a 5-minute break after that, and then sort of continue on for the last 3 minutes. If you have any questions during the lecture, please feel to type them in the chat, and I'll try and answer them as I go along. Otherwise, I might have time in that intermission for a few questions, or I'll be at the tutorial session later. So if you have any questions there, I'll be more than happy to answer them then. So let's get started. Okay, so this is going to be a very brief review of how we actually get gravitational waves as a solution in general relativity. If you haven't seen this before, a good textbook to read through is the textbook by Bernard Schutz, which I've given the link there at the bottom. But very brief, so we start basically with the Einstein field equations. And what we do is we substitute in a form of the metric g mu nu as composed of being a background Minkowski metric, so basically the flat space of special relativity, which we call eta mu nu. And then we say h added to that is some small perturbation, which is going to represent our small gravitational wave. So if you subset that into the Einstein field equations and you work through all the maths, and you do everything to kind of linear order and h, so you don't worry about any of the quantities of second order higher effects, you end up with what's given in equation 1, which is called the linearized Einstein field equations. So you note on the first term on the left hand side is we have this box wave operator, which you'll have seen before from studying electromagnetism, for example, and that's applied to this form h bar, which is very closely related to h. It's just written with some slightly different terms. Then there's a bunch of other terms on the left hand side, and on the right hand side we have the stress energy tensor. Now we can make this equation look a bit simpler by changing our coordinates, which we can always do in GR, and we use a particular coordinate transformation called the Lorentz gauge, where we take our coordinates x alpha and we add some vector psi to them. And if we set up psi in such a way that satisfies the little equation given there, where we apply the wave operator to psi, and that's equal to these derivatives of h bar, where we contract over one of the indices. And it turns out in those new set of equations that that term on the right hand side, the derivatives of h bar go to 0. So we end up with basically in equation 3 in this coordinate frame. And this is usually called the gravitational wave equation, and you can see it's a nice simple wave equation. We have the wave operator applied to some little perturbation h on the left hand side, and on the right hand side we have the stress energy tensor. So in vacuum, we just set the right-hand side to 0, and we have a usual plane wave solution, given equation 4. We write this in terms of this matrix A, which has 10 components, which are sort of our amplitudes of our gravitational wave, and then we have the usual kind of oscillatory term, which is kx with some initial phase phi 0. Now it's interesting to look at this matrix of components A to see what that has. So it's a symmetric 4-dimensional tensor-like object, so it has 10 components. But the coordinates that we're using actually place some restrictions on that. So first of all, the Lorentz gauge itself implies a condition that when we contract A with this wave vector k over one of the indices, we get 0. So that's 4 equations, which then restrict 4 components of A. And it turns out we can do a second very similar coordinate transformation to the Lorentz transformation, except here we're adding a vector chi to the coordinates, which also satisfies the wave equation, except that has 0 on the right-hand side. And you can choose chi in such a way that you have the 2 conditions given by equation 5. The first condition is called the transverse condition, where if you contract A with some vector u, some 4 vector u, you get 0. And on the right-hand side, you have the second term is called the traceless condition, where you take the trace of A, so you raise one index and you sum over that, you get 0. So you know, you've probably heard of transverse traceless coordinates from before, and this is where they come from. And equation 5 basically gives you another restriction on another 4 components of this matrix A. So if you count those up, you realize that there's only 2 components left, which actually have any physical meaning. The rest of the components are basically set by the coordinates. And those 2 components basically represent the 2 gravitational wave polarizations that we have in general relativity, which we'll see in a moment. Now, typically, how we write the solution is in a particular conventional reference frame, which we're going to set up now. So we have a sort of Minkowski-like coordinates, CT, X, Y, Z. We're going to choose this vector u that we had from the transverse condition. We're going to choose that parallel to our time-like direction. And then we're conventionally going to say that the wave is traveling in the plus z direction. So we have our wave vector k parallel to z. And if you work through the maths on that, that sets up various restrictions on our wave vector k, and then our matrix of amplitudes A, which are given in equation 6. And if you substitute those into our solution, you end up with what basically looks like equation 7, where at the front you have our matrix A is now reduced to these two components, A11, which is the on the diagonal, and A12 is the off diagonal, and then we have the wave-like part there as before. So we can do a few more things with this. We can identify a gravitational wavelength lambda and a frequency omega, as is conventionally done. And you can subset those into the exponential sort of oscillatory part of that solution, and you get the equations given in equation 8. So you notice that this both depends on time through omega t, and then there's a z on lambda term, so it depends on the spatial part of the wave. But for at least for terrestrial gravitational wave detectors, so the ones that exist here on Earth, we can do something which is called the long wavelength approximation. So basically what that is that we say that, well, we know the size of our detectors, so LIGO and Virgo, and hopefully one day soon LIGO India. These are only going to be, of all the kilometer size. So the maximum that our wave delta z can change is of order sort of 10 to the 3 meters, but our wavelength of our gravitational wave sources that we typically see has to be at least 10 to the 5 meters, because that's sort of the maximum frequency that we can see up to is about 1 kilohertz. So since that means that our change in z is much smaller than lambda, that means that z on lambda is approximately constant, and we can basically absorb that into our initial phase. So we don't need to treat the spatial part as a sort of separate thing. We can just look at the as a time varying function. This doesn't hold for detectors like LISC, which have sort of million-kilometer arms, and there you have to actually take account of the fact that the wave will actually change in space as well as in time. This is a nice approximation that we can do for terrestrial detectors. Another thing we can do is we can factor into these two basis tensors. So we know that gravitational waves have two polarizations. So you can write this in terms of these two tensors given in equation 13, and then the two amplitudes given by equation 12. And these are conventionally represent the plus and the cross polarizations that we have in general relativity. You might notice in equation 12, there's something a little strange where I've multiplied the A cross amplitude by imaginary number I. That's just to change the phase between the two. So in the vacuum solution, there's no preferred sort of phase between the plus and the cross polarizations. But when you actually looked at solving the Einstein field equations for sort of actual sources, you'll find that typically those the two polarizations are out of phase by 90 degrees. So this is sort of a conventional choice for that to make sense. And another thing we need to do, so in setting up this kind of reference frame, we've basically chosen our vector, sort of a unit vector t, which is our usual Minkowski time coordinate, and then we've chosen z as our direction of wave propagation. But we still only have two unit vectors f, which are the x and y coordinates, which we haven't strictly defined yet. And there's no physics way of doing this, so this is again that's just another convention. And for terrestrial gravitational wave detectors like LIGO, we have the convention given, which is sort of outlined in the diagram on the left, where you say that the celestial equator is basically you take the equator of the Earth and you project that out into space. And then let's say you have you have a gravitational wave coming from direction z, so coming out of the page there. You draw a line through the location where the wave is coming from, that is parallel to the celestial equator, and then the angle from that line up to the x unit vector is called the polarization angle. That sounds very complicated. It's just a way of defining that angle in a particular known way. So this is really just a convention. But then this particularly defines that gravitational wave frame. But one important thing it does is that depending on that choice of psi, that changes how you interpret the polarization. So a plus polarized wave could equally be interpreted as a cross polarized wave, just depending on which reference frame you're using. So it's important to remember that. And then the final thing we have is that when we actually measure gravitational waves, we always measure a tensor. We measure some time series conventionally called h of t. And the measure we model that measurement is that we have a detector response tensor f alpha beta, and then we conject that with our wave solution, and we get some scalar function that we measure, which is given in equation 14. And this defines separate functions called f plus and f cross, which are our detector responses to our plus and our cross polarizations. And they worked out in equation 15, where you contract that detector tensor with our plus and our cross basis tensors. And you can work out an expression for what f alpha beta is, which I won't do here, but it's actually quite a simple expression in terms of the unit vectors pointing along the arms of a laser interferometer. And I've shown you a little example there for LIGO Hanford. Okay, so that's a very brief review of how we have general gravitational wave solutions in general relativity. If that was a bit rushed, that's okay. You don't need to know this in detail to do data analysis. I only learned this material quite recently when I had to actually teach it part of the course. But you can learn a lot from just knowing the basics. But it's good to see where that solution comes from. Okay, so now let's start looking at our continuous wave signal model. So I imagine in Ian's lecture yesterday, you'll have gone through some of the types of sources of continuous gravitational waves in a lot more detail. So I'm just going to briefly outline here some of the typical types of sources that we see in terms of the actual geometry of the neutron star. So we denote that the neutron star is rotating at some frequency f rot. And there are a couple of different models that we typically refer to. So one is called a triaxial or non-axisymmetric rotator, which is a bit of a mouthful. So this occurs when you work out the three principal moments of inertia of the neutron star, which is just comes from classical physics. And you find that those values are all different. So that's why it's given as a triaxial. The name comes from these three components being all different. And this conventionally gives you gravitational wave emission at the frequency which is twice that of the rotation frequency. This is the most commonly assumed model in when we do continuous wave searches. Mostly for the reason that it's the simplest one to do data analysis, because it's really just a single frequency you have to look for. There's another model, which is when you have an axisymmetric rotator or an axisymmetric neutron star, which normally wouldn't give you gravitational wave emission because you need to have some deviation from axisymmetry. But if that system is also freely precessing, then that axisymmetric object will move around in time, and you get emission at actually two frequencies. So either at the rotation frequency plus the precession frequency, or at twice that value. And depending on how this thing is oriented, so how the angle between the angular momentum vector of the system and its axis of symmetry. So if it's sort of off axis, so if the axis of symmetry is at right angles to the angular momentum, you get emission at just twice the rotation and precession frequencies. If the angle is sort of 45 degrees, you get emission at mostly at the single at 1 times the rotation plus precession frequency. And if the two align, you get 0 because it's a purely axisymmetric object which doesn't generate gravitational waves. The last model which gets even more complicated, something called R modes. And I hope Ian gave you a bit of an explanation of this in his lecture, because I find it's a very complicated thing to try and explain. But basically, you can set up a fluid perturbation of a neutron star. So neutron stars aren't wholly solid; they're some sort of fluid objects. And if you can set up a perturbation which is traveling counter to the rotation of the star in a particular reference frame, you can set up a situation where that, instead of that perturbation being damped out over time, it actually grows over time. And the larger it grows, the more rapidly it grows, which is a kind of interesting sort of situation. And because it's a non-axisymmetric perturbation, that gives you a gravitational wave emission. The frequency relationship here is a bit more complicated. It's roughly 4/3 the rotation frequency, but there's about a sort of a 10% error in that, depending on the exact physics, which is a lot more complicated than the other two. So those are kind of the three sort of models of that we have for how sort of a spinning neutron star would emit continuous gravitational waves. For this section, we're going to assume basically the first one is it's the sort of simplest to work with. So let's now actually have a look at what the signal model is. So what is the thing we actually try and measure in a detector? And that's essentially given in equation 17, which you can see is very similar to the model that we just looked at before. So we have two amplitudes of our polarizations, H plus and H cross. We have two detector response functions, F plus and F cross. And then we have one of the polarizations, in this case, the plus being a cosine of initial phase plus some function phi, and then the cross polarization being the same function except with a sine instead of a cosine. So in that equation, I've noted some functional dependence on a few parameters, which I'll go through now, and you'll see how those come into the model in a bit. So probably the most important one is what we call conventionally H naught. And this is the overall gravitational wave amplitude of our signal. And you can write it in the way shown in equation 18 in terms of a couple of parameters. So we have the usual G being gravitational constant, C being the speed of light, D is our distance to our neutron star. The IZZ is again the principal moment of inertia around the rotation axis. And then the final parameter in there, apart from the gravitational wave frequency F, is something which we call the ellipticity. So this is basically when we take the difference between the IXX and IYY moments of inertia, and then we normalize that by IZZ. So it's basically telling us how distorted the neutron star is along these two axes that are orthogonal to the rotation axis. So this quantifies sort of how deformed the neutron star is. And as you can see, when that quantity is 0, then we have H naught is 0, and we don't have any gravitational wave emission. I say that the paper that sort of outlines this in the greatest detail is I've cited in the bottom there is by Jaranowski, Krolak, and Schutz. It's often referred to as because it's quite an important paper, and I feel it's called JKS after the initials of the authors. So if you hear anyone referring to JKS, it's referring to this paper given there. So the question in the chat, yes. So throughout the section, I'm always going to use F as being the gravitational wave frequency. So I won't refer to, so when I've referred to F underscore rot, that's the rotation frequency, but when it's just F, that's always the gravitational wave frequency. And that's usually the case because we only have, for this triaxial model, we only have one emission at one frequency, which makes things simpler. It gets more complicated when you have emission at multiple frequencies. Okay, so H naught is one of the parameters that goes into the amplitudes of the polarizations. The other parameter, if you can see from equation 7, is this angle cos iota. And then this is similar to what we have in a little bit similar to what we have for compact binary CVC signals, where they also have an inclination angle of the orbit. So here it's the angle between the total angular momentum of the neutron star and the direction of the star pointing towards Earth. So when that angle is 0, we're looking at, or rather when the angle is 0, the sort of the vector is pointing directly at us, and then when it's 180 degrees, it's pointing directly away from us. And so given H naught and cos iota, we can write the two amplitudes of our cross plus and cross polarizations. And remember, these are specific to this triaxial non-asymmetric rotator model, and they're given in equation 20. So for different models, for our modes, you would have a different functional dependence, or for this 3D processing system, those expressions in equation 20 will be different. So these only work for this particular model. Again, these are the ones that are most commonly used in the field. So a few properties here that if we have cos iota being 0, that's basically giving us a 90-degree angle, and then we're basically viewing the neutron star as being kind of edge on to its angular momentum vector. And if you look at that equation, you'll see that the H plus becomes 0, so we only have we have H cross going to 0, so we only have H plus. So that gives us linear polarized gravitational waves. Let me just check. No, so if you take equation 18, if you substitute in F equals 2 times F rot, then you'll have 4 times F rot squared, which will multiply by the 4 there, and you get a factor of 16. So the factor of 16 there is if you write equation 18 in terms of the rotation frequency. If you write it in terms of the gravitational wave frequency, then you have a factor of 4. that's it's good to check because it's easy to get confused between the two. I always have to think about it. So thanks for pointing that out. It's a good reminder. So the other situation we have is if we have cost error there being plus or minus 1. So we're either looking directly at the angular momentum vector or directly away from it. This is called viewing the neutron star face on. And in that case, we have the two amplitudes being equal, so h plus being equal to h cross, and then we have circularly polarized gravitational waves. So the difference between linear and circular polarized is actually controlled by the cosine of this inclination angle, not the polarization angle, which also changes between plus and cross plane in a different way. So it's easy to get those two confused. So the final new thing in equation, what was it, 17, which I haven't introduced, is the phase function phi of t. I've written this, and so this is the signal phase as a function of some vector lambda, which are certain represent a set of parameters, which we'll go into a bit later. And then there's two main effects that come into the signal phase. So first of all is the intrinsic evolution of the star's gravitational wave frequency. You often hear continuous wave signals described as being quasi-monochromatic. So they're kind of at the same frequency, but their frequency does actually change as a function of time, which is important to realize. And the second effect that comes into is the relative motion of the detector, which we're assuming is on Earth, relative to the star. So that motion changes the phase of the signal we receive. But let's have a look at the first effect first. So the usual way of writing the signal phase in the neutron star reference frame. So here we've not connected it to a detector yet. We're just looking at the neutron star by itself. And we just write that convention in terms of a Taylor series. So that's given in equation 21. So we've expanded out and I've written here in terms of 3 terms, but in principle you could have more if need be. The reason for that is simply that we suspect that the gravitational wave frequency of continuous wave signals that we can detect tends to evolve slowly over time. So this is different from binary black hole neutron star signals, where the signal sweeps through the band in this sort of chirp model. So here these signals have evolved slowly, so it's reasonable to over a year's observation time to model them as a Taylor series. So here I've written tau. So tau here is the time in the neutron star frame. So it's important to make that distinction. So here I've written, so when I write f without any sort of time brackets, so that's evaluating our f of tau, so our instantaneous frequency that's as a function that evolves with time. So if we evaluate that at delta tau equals 0, that's what we call f. So f is kind of the frequency at a particular point in time, and that's given by t0, which is some reference time that we can choose. So it's important. So that's a kind of a notational distinction to make between when I write f of tau, f of t, that's a function that evolves with time. If I just write f, that's the value of that function evaluated at a particular moment in time. So it's important to remember the difference in that notation. And then we have the 2 derivative terms, which are often written as f dot and f double dot. You also see them written as with a subscript, so f subscript 1, f subscript 2, depending on the notation. But these, again, the derivatives of f of t, that should be f of tau there in the notes. But that's the derivative of the frequency evaluated at delta tau equals 0. So the f dot term there is, and again I've missed the fraction between del f and del t. I'll fix it up later. So f dot is conventionally known as the spin down parameter. Then the name comes from the fact that as our neutron star is losing, is emitting gravitational waves, so gravitational waves transmit energy, And the conventional model is that energy comes from the rotation energy of the star. So as it radiates gravitational waves, it loses rotation energy, and then it starts rotating more slowly. So it's spinning down, hence the name. And the F dot tells us basically how fast it's spinning down. So typically we have F dot being less than 0 for that reason. And then we can also have additional parameters to that. So we have F double dot, which is then our second derivative. And in principle, we can have higher derivatives than that. Now, typically, we only really need a second derivative or higher for very young neutron stars that are much younger than, say, 1,000 years, where we think they might be losing energy on a rapid time scale. But usually for most of the searches that we do, we just assume a first derivative, and that is enough to we hope to find some of the older sources that might be out there. So that's the equation. Basically, 21 basically gives you the model of the signal phase in the reference frame of the neutron star. But of course, we need to then convert that to the reference time of our detector here on Earth, that's where we actually make the measurement. And this is where we have to be careful about changing between different time reference frames. So that's given in equation 22. So if we write our neutron star reference frame time tau, and we write that as a function of our detector time t, we have the equation given in 22 where first we just have t, and then we have a couple of terms which mean different things. So the first term is called as we have a vector r dot product by a unit vector n divided by c, and what that's probably the most important term there, and that's counting for a fact that our detector is on Earth, and now the Earth is rotating. The Earth is rotating on a daily cycle, and it's orbiting around the sun. So as the detector moves around, it's at times going directly towards the source and sometimes directly away from the source. So we get Doppler modulation of the signal. So that term there, the Romer delay, that second term is what accounts for that. So we have R of t being the position of the detector with respect to a point in space which we call the solar system barycenter, which is basically it's the center of mass of the solar system, which is really roughly in the middle of the sun, I guess. Maybe not quite, but at least I've given it there in the diagram. So that's just a point in space, which we can eventually use as a reference, as a sort of origin for our coordinate system. And then our vector n is the unit vector which points from the SSB, the solar system barycenter, towards the neutron star. And that will give us then the sky position of the neutron star, which is often the parameter that we need to search over if we don't know if it's an unknown object. The second term there is d, is the distance to the neutron star. This is usually neglected because we usually assume that the star is stationary or is slowly moving with respect to us. And that's usually a good approximation, provided it's moving less than, say, 1,000 kilometers per hour, I think. But unless you have a neutron star which has been kicked out of a binary and it's moving quite quickly, you can generally afford to ignore that term and just treat it as a constant, in which case it doesn't actually contribute anything. The third term there in equation 22, that only really applies if we have the neutron star as being having a binary companion. So we don't always assume that. We sometimes, in fact, probably more often search for just isolated neutron stars. But if it does have a companion, there's an extra factor of R of t there, which again accounts for the Doppler modulation as the neutron star orbits its companion star. And that has some additional parameters which you need to take into account. So those are the kind of the main factors that go into that part of the signal phase. So now let's go back to our our signal model again, and we can write out, so for an interferometer, and here we're assuming that the arms are at right angles, which is generally the case. We can write out our response functions f plus and f cross in the following way, given equation 23. So we have A and B being functions which depend just on the location and the orientation of the interferometer, which are all known. So A and B are sort of known functions. Whereas the polarization psi is generally not a known parameter a priori, because we don't know the orientation of the source. So that's usually something we have to kind of search over in some sense. So if we take that model in equation 23, we can substitute that into our model before, and we can find that we can write our h of t in terms of the sum over four quantities. I'll give you the expressions explicitly there in equation 25. You don't have to look at those very carefully, but it's just to show explicitly what they are. So the 4a components, the a1, a2, a3, a4, these are known as the amplitude parameters. And essentially because they are the amplitudes of these functions h of j, which are our basis functions. So it's essentially writing it as a linear combination of 4 amplitudes and 4 bases. And then the a are functions of our 4 parameters, which we've already seen. So h naught, cos iota, psi, and phi naught. And then, so that distinguishes those parameters from the lambda, which are the phase parameters. So these are the parameters that come into the phase function that we just looked at. And these are things like the frequency, spin down, second spin down, sky position vector n. If you was in the binary system, we have additional binary parameters and so forth. And we can see that the basis functions are then functions only of these lambda vectors. Now, the reason we make this distinction is quite important because, as we'll see in a moment, because if we look at equation 4, equation 24 is linear in these a parameters, and we'll see that we don't actually have to explicitly search over those. We can do an analytic maximization to find the signal which gives us the best values of those parameters, which sort of maximizes our detection statistic. And that's essentially what the F statistic does, which we'll see in a moment. But that's generally not the case for the lambda parameters. We can't easily have a nice, simple analytic way of maximizing those. So that's when we have to numerically do a search. I'll explain what that entails a bit later. But for the next bit, we're going to look at these A parameters and how we can maximize over them. So the next part of the lectures is going to be on essentially pulling up the idea of match filtering, which is how we actually take our signal model and apply that to data, and then we'll derive the F statistic through that. So we're going to now start working in a discrete data time stream. So we're going to call that X of I, because that's detectors measure, discrete samples of time rather than continuous functions. So we have xi with a time index I, and we have 2 hypotheses that we're going to consider. The first one is our signal hypothesis, where we see our data xi is composed of some function hi, so I here is a time index, plus some noise samples ni. So our hi is our signal model that we've just seen, equation 24. And then ni are some random noise that is part of the data stream. And we'll make some assumptions about the noise. So first of all, assume that each sample ni is a Gaussian. So we'll say that it follows a normal distribution with mean 0 and some variance squared sigma I. And then we'll assume that the samples ni are stationary. And what that means that we assume is that the probability distribution of the noise samples doesn't change, or changes relatively slowly with time. So that means we can essentially pull out the variant, the standard deviation, and basically drop the time dependence of that and just call it sigma. Now that isn't always satisfied, but it's usually satisfied on on some long enough period of time that you can break up the data into those segments and then treat the data as being stationary on that time scale. And the third thing we're going to do is assume that the data are independent, that these noise samples independent. So basically means if we want to do the joint probability distribution of two samples, Ni and L, that's just a product of the individual probability distributions. And one thing that's particularly useful is then you can use that to work out the expectation value of giving two samples Ni and L. And since you can separate those out into the expectation of Ni times the expectation of NL, so for a Gaussian, the expectation value is the mean, and we've assumed that they have mean 0. So that gives us 0 for that result. And we'll use that a couple of times later on. So that's an important result to keep in mind. Again, these assumptions aren't always exactly satisfied for real detector noise, but you can usually break up the data in such a way that's at least on a long enough time scale they are satisfied. So that's our signal hypothesis, and then our noise hypothesis is just assuming that there's noise in the data. So we don't have any signal. Okay, so the first thing we're going to do is look at a single sample xi from our data stream. So we'll look at the conditional probability of xi. So what's the probability of xi, assuming that we have the noise hypothesis? So that just means we're assuming that that's the data, which is purely noise, just follows a normal distribution with mean 0 and variance sigma squared, as we just assumed. And because it's a Gaussian, we can write down the expression for that in equation 27. That's pretty straightforward. Now for the second probability you want to write down is for the signal hypothesis. So if we say the data is composed of some signal plus some noise, if we take our data stream xi and we subtract off our assumed signal hi, then we're left back with the noise again. And the assumption is the noise will then follow the same noise distribution as we have before. So that gives us the conditional probability of our data given the signal hypothesis as equation 28. And it's basically the same as for the noise hypothesis, except we've taken our data xi and we've subtracted off the signal model. So this is kind of how you model the probability of a signal, as you say, well, we subtract the signal off, and then we look at the probability distribution of the noise. That's kind of a nice little trick. So now we can, instead of considering just one sample, we can consider a whole bunch of samples. So we'll say n samples. And because the noise samples are independent, we can just multiply. We can multiply the individual probability distributions together. So that's given in, say, the top line of equation 29. And then we absorb the product of those into a sum over the argument of the exponential. So that's just rewriting that in equation 29. And then the same thing for the noise for the signal distribution. So again, we can just multiply the probability distributions to get our conditional probability of our whole data set. So now, because these expressions are getting a little bit cumbersome, we're going to define a useful kind of inner product, which we can start writing these expressions in. So we'll use a notation of x, y with a sort of dividing line and then parentheses around them in equation 31. And that's basically just taking the sum of xi times yi and then dividing by sigma squared. And so that's the definition for discrete data. And you can also write it in terms of a kind of a continuous analog given by the remaining equations, equation 31. So you can write it in both a discrete way and a continuous way, which we'll use at various points. So just to clarify notations here, delta t is the sampling time of the discrete data interval. We have some overall observation time t, which is n times those normal samples. And another way of writing the noise variance sigma squared is in terms of something called S, which is a single-sided noise power spectral density. So it's basically when if you take a spectrum of a real data set, it's symmetric about the zero frequency. So you can take the negative frequencies and basically add them to the positive frequencies. and that gives you a single-sided spectrum, and the value of that is our single-sided spectral density. That's how it's defined. So then we can rewrite those conditional probabilities again, and except in a slightly more compact way in equations 32 and 33. And from there, we can take what's called the likelihood ratio, and that's basically taking the ratio of those two probability distributions. So the probability of assuming the signal versus assuming the noise, and then working through the math that if you expand out the inner products, you get various terms cancel out. So you'll have on the last line, basically one term which is the inner product of h with x, and the second term which is the product of h with itself. Now at this point we could go further and define a Bayesian odds ratio, which is the probabilities of the actual hypotheses given the data. But all that really does is it takes our likelihood ratio and then rescales it by some prior probabilities of how likely we think the signal hypothesis is relative to the noise hypothesis. But in terms of doing actual data analysis, it's only this likelihood ratio lambda, which is actually a function of the data. That's the thing that we would actually sort of want to practically compute. And basically, we can either treat that lambda as a detection statistic. So what that means is we say that, well, larger values of lambda gives us higher probabilities of a signal, but we don't get an exact, higher relative probabilities, I should say. But we don't get an exact prior odds unless we assume that's constant. Or we can take that lambda and then we can reweight it by or multiply it by that prior odds, and then get a proper Bayesian posterior. So we can always pull on that Bayesian interpretation later if we want to. But for simplicity from here, we're going to work with the likelihood ratio directly. And that the form we're going to use more often is the log likelihood ratio, which is basically taking the logarithm. So it makes it a bit simpler to look at. So the next thing we're going to do is recall back to equation 24. We had the signal model H being in terms of these four amplitudes x, a, j times these basis functions hj. So what we can do is we can substitute that model into our log likelihood given by equation 36. So you basically do that and you expand out the inner products, which are all linear, and you end up with an expression which looks like equation 37, which I've written there explicitly in terms of summing over these four amplitudes. And I'm also going to write it in terms of this kind of dot notation, which is basically it represents a tensor contraction. So that's basically equivalent to having a dot product between vectors or matrix multiplication between a vector and a matrix. So it sort of means both of those things. So equation 37 gives us a fairly nice kind of simple formula for the log likelihood in terms of our vector A of amplitudes. And then we have a vector X, where xj in equation 38 gives us the inner product of one basis function hj with the data. And then we have this matrix M, which gives us the inner products of the basis functions with themselves. So mjk is the inner product of hj with hk. So those are the basis function indices. So one thing we'll note is that x of j is function of the data of both the data and the signal, whereas our mj components, those only depend on our signal model. So there's no x in equation 39, it's just the model h, which we know. So we can compute those analytically. So because I'm probably running a little bit over time, I'm going to go through this a bit quickly, but basically what we can assume is that if we look at those expressions for equation, the basis functions, so they depend on this phase parameter through cosine phi and sine phi, and they also depend on these amplitude functions a of t and b of t. But it turns out that if you think about the phase varies much more rapidly than the amplitudes than these a and b functions, because typically we have the phase the frequency of our gravitational wave being many hertz, so tens, hundreds, even kilohertz, whereas our A and B functions, they only vary on a much slower time scale, which is over a day. So what you find is that when you compute these inner products, that really just depends on the phase of the gravitational wave, and you can get various combinations. So if you take, say, the inner product with H1 and H3, you get a cosine term, which involves the phase, or this omega fast as I've written it there, and then the other term will be a sine, and then those tend to average out over time. Whereas if you take the basis function A1 and you can multiply that by itself, you get a cosine squared term, and that doesn't tend to average out over time. It averages out in here to value of t as you go to higher frequencies. So essentially, what they're saying is that we don't have, so some of these inner products with these basis functions will actually go to zero. So anytime we have a H1, H2 on one side and H3, H4 on the other side, those will average out to zero. So we just need to keep the combinations which involve H1 and H2 with themselves, and then H3 and H4. And those are written in equation 41. So the combinations of H1 with itself and H3 with itself, that's averaging over the A of t detector function, and we're going to call that average capital A. Similarly, for the H2 with itself and H4 with itself, that gives the average of this function B of t with itself, which we call capital B. And then the third term is if we mix H1, H2, or alternatively H3 and H4, that gives us A in the product with A and B, which we call capital C. So after all that, we get this quite nice simple expression for the matrix M, which is written in terms of these A, B, and C averages, which are purely functions of the detector, which have properties that we all know will know from first principles. Well, we'll have no prior knowledge of them. So now that we have that, as I've noted before, we have the log likelihood ratio is a quadratic in this A, these A amplitudes. As you can see on the in equation 43, it's this x dot A plus half A dot M dot A. So we now have to maximize a quadratic. That's pretty easy. We just take the derivatives of the log likelihood with respect to the A parameters, set that to 0. So if you solve that equation, you get the solution that maximizes, so solves that equation, which we can show as a maximum, is our vector A is the inverse of M multiplied by our vector X. So that's given in the second bullet point there. So that's just solving the quadratic function in equation 43. And then making that substitution back into the log likelihood, we get equation 4, and if you expand out all the terms there, you get this term at the bottom, which we have a half times our vector x, which is our data vector, multiplied by the inverse of m, and then multiplied again by x. And this term is exactly what we call the S-statistic. So it's when we take the log likelihood for our signal versus our noise hypothesis, and we maximize over these A parameters. And it's written out explicitly there in terms of equation 45, where you have the individual components of X, you have the A, B, and C averages, and then on the bottom you have something which is usually called D, which is the combination A, B minus C squared. So some notes on terminology here. So when we say match filtering, that's a sort of general term for sort of correlating data against a template, which means different things, slightly different fields. The S-statistic specifically means this sort of maximized log likelihood ratio, which we've worked out here. And adds just a little bit more confusion when we talk about when people actually quote values of the S-statistic, what they usually quote is the value of 2F. So actually twice the value of equation 45. And we'll see what that is in a moment. So I might just stop there for a few minutes since we're at the hour, but we've still got quite a bit to go through. So if there's any questions, please feel free to type them in the chat. Otherwise, maybe we'll start at the hour again in a couple of minutes. Yes, so the priors on the amplitude, that's an excellent question. So I think the statistic implicitly assumes that there are Gaussian priors on the A vectors. So these A amplitudes. I don't remember exactly how you actually derive that, but I think it's the implicit assumption that is made. Now, as a fact, those sort of assumption of Gaussian priors doesn't actually give you nice priors on the physically meaningful priors on the actual physical parameters that they're interested in. So the H naught, cos theta, psi, phi naught, at least three of those have kind of natural priors, like three of them are angles. So you'd assume 0 to 2 pi, or cos theta being between -1 and 1. And then for H naught, you usually want to assume some kind of physically meaningful prior from astrophysics. But yeah, one of the weaknesses of the statistic is it doesn't give you nice priors on those values, which does mean it can be biased to particular types of signals in a way that isn't physically meaningful. And that's why we're doing the proper Bayesian calculation is important. And for many things, like when we look at some signals, or when we follow up sort of a candidate, you'd eventually do that proper estimation to get the values. But as a detection statistic, it tends to work quite well, so that those biases, even though they are there, they don't tend to impact the actual detection power of the statistic very much. There's a paper by Reinhard Prix and Baji Krishnan who worked through this. I forget when it was, maybe 2009. I can find the link later, but yeah, it's true that the amplitude priors aren't entirely physically meaningful in that sense. Okay, I might keep going because we've got still quite a bit to get through. So I might have to go through this relatively quickly. So I apologize. So it seems a bit of a rush. I do suggest that it may be good to sit down in the 2 hours before the tutorial and maybe read through things a bit more slowly if you get a bit lost. But hopefully you can at least follow the gist of what I'm saying, and I'll try not to get into the maths too much. So the next thing we're going to show is something important for any detection statistic, as well as the probability distribution. So how does the F statistic behave when there's no signal in the data, or when there's a signal in the data? So if we do analysis and we find an F statistic value of 2F equals 30, what does that mean? Is that good? Is that bad? Or is that, does that mean a detection or not? We don't really know unless we have that's the context of how is that statistic actually distributed. So to do that, the first thing we need to do is work out the distribution of this vector x. So what we can do is substitute in the signal hypothesis into the equation for x. And if you work through equation 46, you'll see that if we do that, we see that x is given by here the a vectors now the parameters of our signal. So we have a dot product with the jth row of m for the jth value of x, and then we have some product of hj with the noise. So what that shows us is that each xj is a linear sum of our normal random variables, because our linear product is a linear function. So that means the xj is also going to be a normal random variable. But the second thing we must note is that if we take all those four xi, x1, 2, 3, 4 components, those are all linear sums of the same normal random variables, because they're summing up the same noise samples. So they're basically so they end up being correlated normal variables. So that means we have to be a bit careful looking at the distribution. So what we can say then is our vector x follows a multivariate normal distribution with some means mu and then some covariance matrix sigma, and the definitions of those given on the equations there. So we can work what those out. So equation 49 gives us the means. So if we work through and take the expectation value of the definition of x, we get equation 49, and then noting that the expectation value of the noise is 0, we get the equation 50, which gives us the mean of each of the xj. So then if we so it's just a times m, mj, sorry, and then subtracting off the means from x, we get this in the product of hj with the noise. And then we use those expressions to work out the covariance matrix. So then that's written out explicitly in equation 52. And again, so working the expectation value through those terms, you end up with a double sum over the two inner products times the expectation of ni and l, which you hopefully remember is 0 because the ni are independent. So that means we basically pick out the diagonal elements in this double sum. And then on that diagonal element, we have the expectation of ni squared being the variance. So substituting that in equation 53, working through the maths, you find that the covariance matrix is actually equal to this M matrix that we had before. So that's kind of a nice result to get out. So what that says is that X follows a multivariate normal distribution with means mu given by m dot a, and then covariance matrix given by m. And then so now we know the distribution of X. Now what we can do to then find out to make this make finding the full distribution a bit simpler is we can do a whitening transformation to remove the covariance between the X variables. So we'll get some new uncorrelated variables Y. It's a lot easier to work out what those distributions are. So I've given some links there to actually the Wikipedia page is quite useful here. So you can compute something which is called a LISC decomposition. So that's basically taking like a square root of a matrix. So we have this matrix W, which if we multiply it by its transverse, we get the inverse of M. And then if we take our Y being the transpose of that matrix W times X, it turns out that if we do that, then X will if we do that, then we'll find that Y, our new variables, they'll still be in a multivariate normal distribution, and they'll have means nu transformed in the same way, but the covariance will be given by the identity matrix. So now we've decorrelated these variables and we can look at them individually. And the nice thing is we don't actually need to compute W explicitly. We just need to know that we can in principle, as we'll see in a moment. So we can use the definition of Y in terms of X to substitute that into a value of 2F. So here we're writing it in terms of 2F, which we'll see why is for in the moment. And we can see that 2F is basically given by the dot product of Y dot Y. So it's just the length of that vector. Now we know that each of the Y variables are normally distributed with some non-zero mean and some unit variance, as we've seen. And the result that we have from statistics is that if you take the square of such a variable, that will follow a non-central chi-square distribution with 1 degree of freedom. The degree of freedom as a parameter basically means it's the square of one Gaussian variable. But in this case, we have 2F being a sum over 4 variables, the 4Y, so the sum squared of those 4 Y variables, and that will be a non-central chi-square distribution with 4 degrees of freedom. Which is exactly why we refer to F often as being the value 2F, because that twice the value of the statistic has this nice property of following this distribution. And the non-central chi-squared has also a parameter called the non-centrality parameter, which I'm going to write as rho squared, and that's given by the sums of the squares of the means of these Y uncorrelated variables. So equation 5 basically works those out. So it's summing over these means given by the new vector. And if you substitute in the results that we've got before, you get this nice expression at the bottom, which is a dot m dot a, gives you the value of this rho squared non-centrality parameter. And when there's no signal present in the data, we have a being 0, a rho squared is all next 0, and then the value of 2f follows what's called a central chi-squared, or just a chi-squared distribution with 4 degrees of freedom. You may well have come across these distributions in studying statistics before. So we can take the expectation value of the statistic, and we're basically given that result from the properties of the non-central chi-square distribution. It's basically the number of degrees of freedom, which is 4, plus the non-centrality parameter, which is rho squared. That's given in 56. Now, rho squared has another name, which is the optimal signal to noise ratio. So it's basically the maximum value of the detection statistic, or the maximum signal to noise we can achieve when we have our signal and template being perfectly matched in terms of their parameters being identical. So in that sense, it's an important quantity which we'll use later. And then we have no signal present. We have the expectation of 2f being equal to 4. And the plot here just shows what those distributions actually look like. So the solid curve there is when rho squared equals 0. So that's the noise only distribution. So you can see it peaks around 2, but the mean of it is actually 4, and that sort of tails off as we go to higher 2f. And then as we increase rho squared, we get the values, the distributions being peaked kind of at higher values, but also being kind of more spread out. So that's how those curves kind of look like. Right. So the final major thing I'm going to try and cover in the lecture is going to be on template banks. And something called the parameter space metric. So just quickly go through this. So I know before that we have this distinction between the A parameters, the amplitude parameters, and the phase parameters, which are called lambda. So as we've seen, the nice thing about the amplitude parameters is we can analytically maximize over them. So we get this thing called the F statistic. So we don't have to never explicitly choose those values. The F statistic basically gives them to us. But we can't do the same thing for the lambda parameters. So we basically need to do what you could say is a numerical maximization, what we call basically a search over lambda. So basically what we do is we evaluate 2f at different choices of lambda, which I've called their lambda I. Each of those lambdas is called a template, and then if you take them as a set together, they're called a template bank. So we're basically picking different values, and then we're computing the F statistic of each of them. And in principle, we'd find when we find the value where the 2f is maximum, we'd say that's our best candidate for a CW signal. In practice, because our detector is not perfect, they have instrumental noise of various types in them. We usually choose some threshold, and we'll keep all results above that, which we'll then study further in detail. But the missing ingredient here is how do we actually choose which templates to evaluate 2f at? So obviously we can't choose an infinite number of templates because each of them take a finite number of time to compute, because we actually have to analyze some data, and we only have a finite number of computers. So one thing you might be concerned about is that suppose we had some signal in the data which has parameters lambda s. So what if that lambda s didn't exactly match any of our templates? Would that mean that we failed to detect a signal? The good news is that isn't necessarily the case, because our templates, the templates that we search, these lambda I, they're in some sense fuzzy. So we'd only have to get an exact match to our signal parameters in order to make a detection, which is good. The caveat is that if we don't get an exact match between our template and our signal, we won't recover the full power that's present in the signal. So if we evaluate our signal to noise ratio rho squared at one of our templates, that'll be less than if we evaluate at the maximum value, which is given by rho squared at lambda s. So we can quantify that relative loss between the two, when we have the signal not matching directly the template, we can quantify the relative loss of rho squared by this term called the mismatch. So the mismatch is defined in equation 57. We basically take the difference between our rho squared at our exact match, lambda s, and we subtract off the rho squared at our template, which is different, which is not going to be exactly equal to our signal. Then we normalize that by our maximum rho squared at lambda s. So the mismatch is the quantity between 0 and 1, strictly speaking. So how we actually build our templates is we choose our lambda I in such a way that for any signal we have in the data, so whatever parameters there are, we always have the mismatch between, we can always find some template, lambda I, where the mismatch between that template and the signal is less than some maximum. I may have spent, that'll become a bit clearer when I have a diagram on the next slide, but basically, so we have this parameter lambda max, which we can choose to we basically have a choice to choose what that is. And there's different trade-offs. So if we have a smaller lambda max, we have better signal recovery, but we'll also have more templates and we'll have higher computational costs. So hopefully this little diagram will make it a bit clearer. So here we have 3 sort of example templates which have some spacing. And the sort of colored curves here is basically the mismatch that falls away as we move away from each template. But you see they've been positioned in such a way that sort of when the mismatch from one template reaches here mu max, which is 20%, it's then start to recover by the next template. So if you follow the red line, as that falls towards 20%, then they get picked up by the blue line, and then by the orange line. So we've constructed this template bank in such a way with choosing our delta lambda that our mismatch is always less than 20%. So it doesn't matter where the signal is, we'll always recover it with that amount of mismatch. So we can do that, and that's quite a good way of doing things. The one thing we need though is some algorithm to determine what that spacing is, given our lambda, given our mu max. And that's where this concept of a parameter space metric comes in. So we basically use the metric as basically a distance measure, which exactly gives us this mismatch. So in equation 59, the metric here is some tensor G alpha beta. And then if we have some differences delta lambda between our template and our signal, we work out the right-hand side of that equation, and that gives us the mismatch. And there I've given you an example of how we'd work out these template spacing for that little example. So this is a really useful tool. The next thing to do is how do we actually get that value, work out that value of that tensor G alpha beta. Now that doing the full derivation of this for the F statistic is actually pretty complicated. If you're interested in seeing that, there's I've cited the paper by Reinhard Prix there, which gives the full calculation. So what I'm going to try and skim through is basically a simplified derivation where we assume we just have a 2-component signal model. So we don't have the 4-component model that we have in continuous gravitational waves. We just have basically a simple sinusoid. So we have a single parameter A multiplied by some e to the I phi naught plus some phase. So in that simplified model, we give you can work out what our inner products X are, and we'll still have two inner products because we have 2 parameters A and phi naught. And in that model, the F statistic simplifies down to equation 63. So on the top we have our sort of inner product with our single sort of template H, which I'm just going to call X, and then that's normalized on the bottom by what used to be our inner product A, if you remember from the matrix M. But you can basically take equation 63 as basically the simplified version of this statistic for just this simple sinusoidal model. So you can work out the expectation value of that, and I'm not going to go through this in detail, but you basically sort of substitute in the value of X and expand that out, and what you're left with is in equation 66, you can get the optimal signal to noise ratio at a particular template lambda, which is given the equation on the right hand side of 66. Notice this differs a little bit from the definition for the expectation value of the statistic for our full model, which is, if you remember, is 4 plus rho squared. In equation 66, we've assumed it's 2 plus rho squared because we only have 2 components. But basically, the right-hand side of equation 66 is what we're going to work with. And then what we do is we do a second order, we do a Taylor expansion of rho squared around our position of our signal, lambda s, and then we do that as a second order Taylor expansion. So that's written out in equation 67. Where I've written for sort of shorthand, this notation del alpha just means the derivative with respect to the lambda alpha phase parameter, and then del alpha beta is the second derivative with respect to lambda alpha, lambda beta. Well, I'm missing a del there, but I'll fix that up later. Okay, so the first thing we want to do is work out the first derivatives of rho squared. And we can work through the terms there. I've written in terms of our quotient of terms u and v. So we can apply the quotient rule for doing our derivatives. And they're written out in equations 68 and 69. Now you have to be very careful here because you have to do the differentiation first with respect to lambda, and then evaluate that at lambda s. So you have to get those things around the right way. But essentially, if you work through the maths, which is lined out there, what you'll find is that the first derivative of rho squared ends up being 0, which if you think about it exactly was what we'd expect, because the definition of our rho squared is that it's maximized at when our signal and our template are perfectly matched. So that's the definition of our optimal signal to noise ratio, which we saw before. So you'd expect that being a local maximum to there being no derivative at that point lambda s. So that's good. So the second thing to do is then do the second derivatives. And again, you can write that in terms of quotient, in terms of some variables w and z. You can work through those. There's some simplifications you get because the w ends up being 0, basically from the results on the previous slide. So you end up with equation 73, where you just have to work out the derivatives of w, which is a little bit complicated, but it's really just working through the maths on equations 72, and then evaluating that to the right place. And if you do that, you'll find that the two of the terms in w. Sorry, I'll go back again. If you look at the first and the last term here in equation 72b, the derivatives of those gives you this expression in equation 74a, whereas the remaining two terms in w, they end up being 0 when you evaluate at lambda s. So that simplifies things a bit. So you get then the second derivatives of rho squared being the expression given in 75, which isn't looking too bad. So if you then take that expression and you substitute that into our Taylor expansion for the mismatch, so remembering that the first derivatives of our rho squared being 0, we can write the mismatch mu as just being the right-hand side of 76. So we just have the second derivatives of rho squared, and then it's normalized by rho at lambda s, which you can work out in 77. And then substituting all those things together, we get in equation 78 the form of the mismatch we're after in terms of this this G tensor, and the full expression for that is given in 79. So this is in terms of various inner products of our signals of basis function h, and we have sort of that differentiated with respect to the various phase parameters. Again, this just follows from doing sort of simple differentiation as was shown on the last slides, which I skipped through. But we can simplify equation 79 by quite a bit if we actually spanned out the forms of the inner products. You can use the sort of continuous version here, so we're going to write them as integrals on the first line of equation 80. And then if you remember, the h here is just an exponential, so it's an exponential of e to the I phi of t, phi of lambda, sorry. So when you differentiate that with respect to lambda, you get some derivatives of, here you get a derivative of phi with respect to alpha, and then derivative of phi with respect to beta, which come out of the exponentials. Otherwise, they stay the same. And remember, because we've used the sort of complex notation here, we need to make sure we take a complex conjugate of at least one of the sides, which means that those two terms, the e to the I phi 0 plus phi s terms basically cancel out. So that gives you the third line in equation 80. Then on the bottom on the denominator, you just have the integral over 1, which is time, t, capital T. So it turns out just working through this, and you can do this more carefully yourselves, you find that this sort of ratio in the product is given just by this integration of the derivatives of the phase, which we can write there in terms of a time, the sort of angle notation in terms of a time average operator, which is given in equation 81. And you can show the same thing for some of the other products. So you basically have the result in equation 83, where the metric is given, and there's relatively simple terms involving just the derivatives of the phase with respect to the various parameters. And then you do this time integral. So this is a well-known result in the field, which is the phase metric approximation. It's called phase because it always just depends on the phase. And you might think this is a bit of a sort of a simplified result because we've only assumed this sort of very simple sinusoidal model. But it turns out this is a very good approximation to the mismatch, even for the full component, four components continuous wave model that we use to do searches, provided we search over much longer than a day, which we usually do. We usually look at a year's worth of LIGO data. And then in that case, these A and B amplitudes, which are then put on the full model, they tend to kind of average out. So equation 83 is actually a very useful tool and something we use all the time to build our template banks. So since I'm running close to time, I'll go through this quickly. So you can expand out go back to the phase model for an isolated neutron star. So we won't have the modulation due to the companion, and we'll just say we have one spin down parameter. So if you look back at one of the earlier slides, you get the phase model for that system. You can span it out. There's a few terms for the purposes of computing the metric. You can simplify things by dropping a few terms which end up being small. And you end up with expression given in equation 86. So you just have a f delta t plus half f dot t squared. So that's the kind of the part that accounts for the phase modulation, the spin evolution of the neutron star, and the third term accounts for the Doppler modulation due to the fact that the detector is moving. So this is a kind of simplified model we can use to calculate the metric. So now what we're going to do is we're going to work through actually computing. So we're going to assume that this part here, the n vector, is known. So we won't worry about the Doppler modulation part, and we'll just calculate the spin down metric, which is called in just the f and the f dot parameters. So we know what those. So we can do that all analytically. So we can work up the derivatives of the phase with respect to f and f dot in equation 87a. And then just work through those expressions. You get some terms given there in terms of the observation time capital T, and then this reference time T naught. And these expressions actually become a lot simpler if you assume that the reference time T naught is basically in the midpoint of our observation time, which we say is from 0 to T. So we say that T naught is capital T divided by 2. And you get the expressions given in equation 88. Which are actually quite simple. So we have for the GFF terms, this is the frequency, we have pi squared t squared on 3. The f dot cross term, that goes to 0 when we make this choice of reference time, and then the the term for the spin down derivatives is just pi squared t4 on 180. So these are pretty nice simple things. And an interesting property to note about the metric is that these expressions are independent of the parameters themselves. So there's no dependence on f and f dot in these expressions, which means at least in terms of the spin down parameters, the density of the templates you place doesn't depend on your location and parameter space. So it doesn't mean that say at higher frequency you need more templates, and at low frequency you need lower templates. The density is the same all the way, which is highly desirable, because that means you can basically use a kind of regular grid, or in higher dimensions a regular lattice, to generate your template bank in an efficient way, and that way you can optimize to reduce the number of templates that you need, because the metric has this nice simple form, which makes it easy to do. And I think I'm onto my last couple of slides here. So this is giving a little example of how you do this for a work out the spacing for a square grid. So here I've done a little cartoon of a template bank in frequency f and spin and f dot. As you can see, it sort of continues out to infinity, but I've highlighted some colored templates in various colors there, and I've indicated the spacing between the template points. So the equation for these ellipses here are called the metric ellipses, and they're basically plotting this equation where you set the metric equal to our chosen mu max, which you can write that explicitly in equation 89. Now, to actually work out the spacings, there's a property of the square grid, which in sort of mathematical terms is called a Z2 lattice. Z here being for the space of integers. So for Z2 lattice, we have each of the dimensions contributing equally to the mismatch. So we can actually divide up the equation for the metric in equation 89 into two separate equations. I'm not sure why the equation numbers there are the same, but so you can basically write that both g of f times delta f squared is equal to mu max on 2, and the same for g f dot times delta f dot over 2, and those are easy to solve for getting the metric spacings delta f and delta f dot, which is something we'll need to use for the tutorial. Okay, so that's all I wanted to cover. I'm sorry that got a bit of a rush towards the end, but I would suggest going through and reading through it a bit more carefully before the tutorial. But hopefully you've got the gist of what I was trying to say. And the remaining slides are just I put together some reading lists on some papers that you might be interested in if you want to read for the study. So that's it for me. So thanks for listening.
Thank you, Karl. It was really nice talk. Aditya has a hand for questions.
Thank you, Karl, for the talk. I have two broad questions.
First is, sorry, I'm having trouble hearing you. Could you?
Is this better?
Yes, that's much better. Thank you.
Yeah, thank you. So my first question is, you made the assumption of non-stationary and Gaussian noise, but we all know that generally, especially over long time periods, the noise is hardly Gaussian or stationary. So what are the ways in which we can sort of relax that assumption? How would it impact stuff that you sense calculation of the F statistic or something like that?
Yeah, that's a great question. So what is usually done is that you'll break up the as I indicated, you break up the data into smaller pieces where you can essentially make that assumption. So typically what we do is we break up our data into segments which are 30 minutes long. And there's a few reasons for that. 30 minutes is about the longest period that you can assume that a CW signal is exactly monochromatic. If you go beyond 30 minutes, then you have to take account that effect that the Doppler modulation due to the Earth's rotation is actually modulating the signal. But over about a 30-minute time, you can assume that the signal is basically a constant frequency. That's very useful for a lot of different algorithms, which may just some do a power spectrum and basically sum at that exact frequency. And the other reason for splitting up in that way is that as over those 30 minutes, you can basically assume that the sort of noise floor of our detectors is going to be roughly constant. So so it's usually that the stationarity is the problem that we have to worry about. So so over time, obviously, the detectors often get more sensitive as commissioning goes on throughout the run. So so we can't assume that there's a single the same variance of all the noise samples across that time. But what you can do is say over that 30-minute time that has the same noise spectrum, and then the next 30 minutes they'll have a different noise spectrum. And then you can do the same calculation as we've done before, but what you need to do is just you sort of weight each of those 30-minute segments by the relative noise floor that they have. So you can sort of generalize this the calculation that we went through in that case, but instead of having a single variance or single noise floor, you have a kind of a weighted sum over the data. And that's usually good enough to account for the sort of stationarity. The other problem we have to avoid, which we again assume that the data is nice and Gaussian. Of course, it isn't. We have all sorts of both time dependent sort of glitches and also sort of frequency instrumental lines from various things. The usual way of doing that is you don't try and model those in the actual data analysis method. This is obviously very hard to model sort of a complicated spectrum of a LIGO detector, or Virgo or LIGO India. But what's usually happens is you'll calculate your statistic, and then again you'll have a closer study of the values of, say, the F statistic you get, which are kind of large, but you then need to look carefully at the data and say, okay, we've seen some loud value, but is that close to, say, an instrumental line? And often what we'll see is that there'll be say you'll get a loud result, but there'll be, say, a loud value at, say, Hanford, because there's an instrumental line that happens to be there in the spectrum, but in, say, Livingston, there isn't a line there. So you'll get an effect which is where you're basically seeing something from just one detector, and those are easy to kind of veto because we'd assume that a true gravitational wave signal will be present in both detectors. So it's really dealt with by doing kind of a post-processing of the data after you've done your initial kind of search, and it's just something we have to deal with. But yeah, in terms of the non-stationarity, we can sort of basically do that by doing this sort of weighted average.
Thank you. I have one more question, but I'll probably allow others to ask.
Shash, please go ahead.
Yeah, thanks, Karl, for the nice talk. My question was specifically regarding how sensitive the searches are to specific modulations in the waveform. So, say for example, if you were to do a search where you assume that the spinning neutron star is isolated, would that search be able to pick up a signal from, say, a system which is part of a binary, or would it completely miss it? That's just an example, but there are like other modulations of this nature. I was just wondering how sensitive the searches are to such things.
Yeah, no, that's an excellent question. So it really depends what the parameters of this particular search that you're doing. So for most of the searches that say look for kind of an all sky survey for isolated neutron stars, they'll typically try and search, basically down to the kind of lowest frequency, maybe sort of 10 or 20 hertz, and then maybe try and go up to at least sort of a kilohertz in frequency, maybe 1500, or even further than that. But that's kind of the typical range in frequencies. For the spin downs, it tends to vary a little bit, but typically something like 10 to the minus 9, 10 to the minus 8 is the kind of typical frequency, the spin down range that those searches cover. Now, in terms of the sensitivity for binaries, so what you can do is that if you think about the binary modulation, that's going to be some sort of circular kind of modulation. So you have some cosine and sine terms. So what you can do is you could take that R term, which I had there, R of tau, I think it was, from the equation, and you can do a Taylor expansion of that. So you can expand that in terms of the powers of time. And then what you'll find is that then that modulation will start to look like the frequency and spin down modulation that we have, which is intrinsic from the neutron star. So that means that in principle that that the searches we do can actually pick up that type of signal, provided that we can do that, provided that Taylor expansion is actually valid. So the regime where that will be valid would be if there are long period binaries out there. So systems which I mean, you see that to be sort of looking at a period which is sort of longer than the time that we observe for. So we typically look, as over years worth of data. So let's say a continuous wave signal from a neutron star, which was in a binary with a period of say 10 years. That would be long enough that we could, that the modulation due to the binary would be small enough that you could do this sort of Taylor expansion. And then the model that we have would be sensitive enough to that. So essentially, to answer your question, we are sensitive to those types of those systems, but well, let me be clear. So for the searches that we do for isolated neutron stars, they would also be sensitive to stars which are kind of in long period binaries. So we're long being sort of longer than a year or so. But otherwise, if you want to look for things which have periods which are much shorter than a year, then you have to model that orbital motion of the binary explicitly, and we do have searches that do that. It's more complicated to do because the binary modulation adds between 3 and 5 additional parameters which you have to search over, depending on whether you say it's a circular orbit or it's an elliptic orbit. So that makes your parameter space larger. It makes the computational cost much higher. So we can't do searches which are kind of as sensitive for those because we have a larger parameter space to cover. But we do have algorithms that do them, and we use them to analyze O3 data, for example.
Thank you, Karl.
Nice.
Aditya has a follow-up question in the chat. He asks, are there techniques to search for unmodeled signals in the data, unmodeled continuous wave signals?
Yes, there are a number of them. So as you said, most of the methods that we have assume something like this phase model, but there are ones that have different sensitivity to. So the algorithm we went through in the lectures is this match forcing, which assumes you have full phase coherence between the template and the signal, so over a year's observation time. And the advantage there is that's very sensitive, but also it adds a lot of it makes the search very expensive because that makes it very sensitive to small changes in the phase. So basically, what you find is you work out the metric that scale the metric as you've seen the metrics of scales with the powers of time. So as you increase your time, you have to put more and more templates, and it becomes quite expensive. So there are different algorithms which do different trade-offs. There's a sort of paradigm for doing this, which I didn't cover, which is called a semi-coherent algorithm, which is essentially you break up the data into these little blocks, as we were talking about before. but then you just look at the power of the data over that 30-minute interval. You don't look at so you basically throw away the phase part, and that makes you less sensitive to some to kind of how the phase changes between sort of one 30-minute block to the next. But it means you can actually do more sensitive searches that way, because you the metric on that type of statistic doesn't scale quite in the same way. It doesn't scale as steeply as the power of time. So so the semi-coherent sort of paradigm is one that we use most often to do actual searches, although they're built ultimately on sort of match filtering and the statistic that we've described here. So things like the power flux algorithm, sky half, frequency half, if you've heard these names mentioned in papers, they're basically based on this sort of paradigm. But one thing we've had recently is some algorithms which are completely unmodeled, which look for basically kind of wandering signals which are going to start wandering around kind of stochastically. And this came from a collaboration at the University of Melbourne with some electrical engineers who knew about this algorithm called Viterbi, which is basically a kind of a smart way of tracking a sort of signal through a time frequency plane, where you kind of it looks at all the possible combinations, but in a sort of smart way where it only picks up ones which are going to be maximum when you get to the end. So instead of doing kind of all sort of if you sample all possible combinations, you get some kind of exponential thing which grows very rapidly, but this kind of has a smart way where it can kind of do this tracking in kind of linear way with time. So we have that. So that's been kind of a recent thing that's been developed. One of the reasons it's developed was looking for some systems where we have a continuous wave signal in a binary, but there's an accretion from the binary companion onto the neutron star. So basically a low mass X-ray binary. And what that accretion can do is that sort of varies the torque on the neutron star, and that means the frequency can kind of vary around over some time scale, which is difficult to model. So the Viterbi algorithm was developed to kind of have that phase tracking, but it's also something you can apply just generally to the LIGO data stream, and you might find, a CW signal which isn't following this sort of nice kind of Taylor expansion model that we've been assuming. Of course, the downside there, of course, is that you find all the sort of noise factors, but also the noise disturbances which also kind of vary around in frequency. But yeah, there are certainly ways that you can move beyond having this phase model approach, but it tends to be kind of a trade-off of sensitivity versus robustness. So you can be very sensitive if you have kind of an exact model, or you can be robust to have this kind of more general kind of tracking thing, but it's hard to do both at once. So we kind of try and do sensitive searches, and we try and do sort of these phase wandering robust searches as well. So to sort of cover our bases.
Thanks. I just had one clarifying question. So when we do say directed searches or targeted searches, the sky location parameters is within the lambda parameters, or it's within the amplitude parameters? Like, how do we tune our searches for those, depending on how much information we have?
Yes, so there's a type of search we do which we call directed searches, as you said, and what that basically means is that we're looking at something where we're looking basically at a known astrophysical object. So we have something that we see in the sky, so we have a sky position for it which is relatively well known, but we don't know anything about the frequency evolution. So we don't know what the F and the F dot is. And the classical example of that is when we look for supernova remnants. So the idea here is that there's a supernova remnant. So there's obviously been a supernova. There's been a star that's been exploded, and maybe hopefully it's collapsed into a neutron star. That neutron star is kind of young. It might be doing things, and hopefully it's maybe radiating gravitational waves. But often we don't see these things as a known pulsar. So we don't see a radio or an X-ray kind of pulsations from them. But we often see we'll often see the neutron star as a kind of X-ray spot, so you can measure the sky position of that very precisely. So for those types of searches, we can basically if you go back to the phase model, that term r dot n on c, that basically becomes a kind of known constant. So we only need to worry about then the f and the f dot part. And there's a few things like Cassiopeia A is a classic example where we know the sky position very well. For some of the other searches, we don't see an X-ray spot there. We just see the nebula, but we don't see a sort of bright X-ray spot. So we don't know. Maybe there's a neutron star there, but maybe it's the star completely disintegrated and there's just nothing left, or the neutron star was flung out of the nebula and it's off somewhere else. So there we don't know the sky position as precisely, but it's usually the case that we know it well enough that we can just point a single point. We'll do a single pointing, if you like, at that particular point in the sky. So we assume that the n is kind of a known value, and then it no longer is part of the search in the sense. It's kind of a known constant. But yeah, for some of them, they're not. The position is not known precisely enough that you may have to look like at a few different sky positions around, but that's easy enough to do.
I see. Thanks, Karl. I think there are no more questions. Thank you very much. It was indeed very interesting and informative talk. So I request all of you to be at 4 here. So we'll do the tutorial session.